Okay, we're recording, and we are going to get started with looking at Canvas and looking at uh, the whoa, what's it called? The study guide. Yeah, that's the word for it. Oh, and I'm sorry about Tuesday about the FizCon. I have a heart arrhythmia that sometimes pops up, and on Tuesday it was just going crazy, so I had to go to the doctor just to be sure that it was okay and that I wasn't having any like weird symptoms of, like, let's say coronavirus or something. But it's all good, it's all okay. So I'm sorry I added to your to-do list with asking you to watch those videos, but thank you for doing it because you'll need that stuff in order to do the workbook anyway. So here we have, oh, one thing I want to remind you, here's a whole module called Exam 1. So right here is where it says Exam 1 and Walters 122. If you click there, that's where you would have you could like see more about your score and how I broke down the points for you. And then here where it says Exam Wrapper or Exam 1, that's where you submit the exam wrapper. You have to have collected your exam from me to submit that. And so be sure you submit that. I would like to see it before our exam on Tuesday. And here's where you can submit your revisions for your exam. So if you want to do your revisions for the exam, there are some questions I'm asking you here. I give you your instructions here. So you can submit those electronically. And I am happy to help with those revisions if you're stuck. I want you to work on them first. But if you're stuck and you don't know what to do, I'm happy to help with those in my office hours. Questions about this exam will come first before questions about the review, but I'm happy to help on those, okay? All right, so down here under, this is our week 8, where it says Thursday goals, you found the meeting, and right here, face-to-face exam 2, get your study guide here. Here is where you can find the study guide. Here is a little PDF of some kind of conceptual type questions, kind of like what you might see on the exam. It's not all encompassing. There are going to be a few that I'm going to select from this list, okay, but not all of them. And then, and they won't be exactly like this. They'll be somewhat different. Like I might ask you, instead of a positive charge, maybe I'll ask you about a negative charge, for example. So you can take a look at those if you're curious. Your equation sheet and then the rubric are all here. Okay, so let's just jump right in with our, just looking at the study guide, and then I'm gonna walk through a bunch of problems. We're gonna practice some kinds of conceptual questions as well, okay? So, Walters 122, I'm gonna separate you into the 3 groups again. You get first choice of where you wanna sit. I'm gonna open the room at 9 a.m. on Tuesday so that you can get settled and you can get yourself ready. No phones out, but you can use your calculator. You get your whole exam period, same thing, 100 points. We've got 10 multiple choice worth 2 points each. 4 free response that are worth 20 points that I'm using that rubric, the same one you've seen already, to grade. And so I think the rubric was fairly effective in kind of getting you all to think about what you need to do to demonstrate to me that you understand the problem solving process. So please use that to help self-assess yourself. And I think if you're using that to self-assess as you're working through the problem, then it will be, you'll be more likely to get more points for yourself. Okay, so let's just talk about all these concepts. On these that say concepts to understand, these are just things, things that will be part of the free response questions, but also things that could be incorporated or will be incorporated into our conceptual questions. If it's not on here, it's not on the exam. So for example, on here, I'm not asking you anything about the RMS voltage and the AC current. That's not on the study guide, so it's not going to be on your exam, for example. All right, so the first thing that we started with when we began our study of um, I'm calling this unit electrostatics and electrodynamics. We're thinking mostly about individual charges, and then later some of those charges start to move, okay? And then next unit, we're gonna have full-blown circuit and then magnetism. But the first thing we started with was thinking about charge. Charge is quantized. That means you can only have an integer number of charge. Like you can only have one proton, you can only have one electron, or 2 electrons, or 5 electrons. You can't have like half an electron. And I'm going to ask you to be sure you understand the charge or know the charge of a proton and an electron. And if you it's okay if you don't have it memorized because it's on your equation sheet. So become familiar with your equation sheet as best as you can. When you're working on your problems, always have this out so that you can get familiar with where things are located. On the front, all I tell you is the charge on the electron, and it says minus 1.6 times 10 to the minus 19 coulomb. The charge on a proton is positive 1.6 times 10 to the minus 19 coulomb. So that specifically is not on here. All you get is the fundamental charge, the charge of an electron, but it's just positive, that value for the charge on a proton. Understand how charge can be transferred between initially neutral objects. So in that very first mini lecture, we talked about how we have insulators and we have conductors. And if you take 2 objects that are neutral, when an object is neutral, it has the same number of positive and negative charge. But you can take 2 neutral objects and you can rub them together. And whenever you rub them together, depending on the properties of those things, you can transfer charge. So one of those objects can become positively charged and one can become negatively charged. The one that becomes negatively charged, that just means it essentially is stealing electrons from the other object, and it gets an excess of electrons. The other object essentially has a deficiency of electrons, and so now it's a positively charged object. The same number of charge that was in our whole system is the same as before and after, but we've just transferred some of that charge from one of the objects to the other. Why don't we, okay, and then know the properties of insulators and conductors, and in particular, how charge is distributed on a conductor. So I very briefly talked about that when I talked about, I talked a little bit about how charge can be distributed on a conductor and how that can help us whenever we're in a car in a lightning storm, for example. So let us, I've got 2 questions, conceptual questions that kind of go along with this. So I'm just gonna launch those now, and then we can talk about the answers to those, because these are kind of conceptual questions that are based on these ideas right here, similar to what you might be asked on the their exams this semester. Let me, yes, I'm gonna launch this one. Okay, so you have 2 electrically neutral objects and we are rubbing them together. After this process is complete, the net charge on one of the objects is positive Q. What's the net charge on the other object? Oh, excellent. Cool, I'm just gonna wait 10 more seconds. All the answers coming through are good. Okay. So everybody who voted said negative Q. Good. We had the same number of positive as negative charges to start with. If we start transferring the charge, one of those objects is going to get an excess of charge of negative charge, and the other is going to get this an excess of positive charge, but the number of excess charges on both of them is the same, or the number of excess and then the number of depleted charge. Okay, good. So I could ask you that question in a couple of different ways, but that's something that you might see. And then let's look at another one. Let's see. Here, this one might be less obvious. Okay, so which of the following is an accurate statement about conductors? A conductor cannot carry a net charge. If a solid metal sphere carries a net charge, the charge is distributed on the surface of the sphere. Or if a solid metal sphere carries a net charge, the charge is distributed evenly throughout. So we don't have any, there's no current here. It's just that this object has some, could have some net charge. And if it did, where would that charge be? Okay, so let's launch this. So this one was less clear. Okay, let's see. So which of the following is an accurate statement? So a conductor can absolutely carry a net charge. We can transfer charge onto a conductor. A conductor is something that conducts electricity very well. It has a lot of free electrons that are free to transfer, free to move between objects. So a conductor can have a net charge. And if a conductor has a net charge, that charge distributes itself such that all of that charge is distributed on its surface, not uniformly within it. So we did briefly mention that there is one slide, actually 2 slides about this. And we talked about how if you're in your car during a lightning storm, if that lightning strikes you, the charge gets distributed on the surface of your car. That car's shell is the conductor. And then that protects you inside, makes you safe. So yeah, the charge should be distributed on the surface. And this also plays into a little bit about how lightning rods work. So, and you can read also about this in your textbook. So the answer here should be the middle one. The charge is distributed on the surface of the sphere. Okay, so that's some of these things about electric charge here. And then we started talking about electric force and electric field. So it's important to understand the difference between electric force and electric field. And when we do this section and when we do this exam, one of the biggest things I see students mess up on is that they don't read the problem carefully and they work the problem for an electric field when I'm asking them for an electric force and vice versa. So understand the difference between electric force and electric field. Now in chapter 18, there were only 3 equations we have on our equation sheet under chapter 18. We've got Coulomb's law. That's the electric force between charged objects. That's our K, Q1, Q2 over R squared, okay? The electric field is E equals the electric force divided by charge. So the electric field is an electric force per unit charge. The electric field is the force per unit charge experienced by some test particle due to the presence of another charge. And the electric field for the point charge is also kq over r squared. So there's a little bit of a difference there. The force is like a push or a pull, like we had last semester, but this push or a pull is due to whether you have opposite charges or like charges. So we remember that for electric force, you have this push or the pull that happens because either you have two like charges or more, or two opposite charges or more. So the electric force between two like charges is repulsive. It's going to want to push those charged particles away from each other. And then the force between two unlike charges is attractive. So if you have a positive and negative charge, they're going to want to pull together. If you have a positive and positive or negative charge, they want to push each other away. So we want to be able to apply Coulomb's law, which is the electric force between two charges, to solve for, that force, that quantity. We also want to understand that the electric force varies with distance, or understand how that electric force varies with distance. And we've got the electric force is inversely proportional to the distance squared. So the further away those charges are from each other, the weaker that electric force is going to be. And then, so with our force, the electric force vectors, if we have attractive forces, those electric force vectors are pointing toward the positive and negative charge, pointing into each other like this. If we have like charges, those electric force vectors are going to be pointing away from each other. Okay, so those are the rules for electric force vectors. For electric field vectors, the electric field vector always points away from positive charge, but toward negative charge. So if I ask you to draw the electric field at some point around a positive charge, because that's a positive charge, the electric field vector is always going to be pointing away from that charge. If it's a negative charge and I ask you to draw the electric field vector around it, those vectors will be pointing in toward the negative charge. We also want to review our rules for electric field line diagrams. I will ask you a question. I will give you some charges. I'm going to draw the electric field lines around them, and I'm going to ask you which of those charges is positive and negative, and then to tell me about the relative magnitude of those charges. Remember that the more closely packed in that those electric field lines are, the greater the magnitude of the electric field at that point. Let's see. Know how to find the electric field magnitude and direction that it points at a location away from a charge. This is one of our 4 free response questions. So we will do an example of this, okay, in a minute. And then, we already talked about this, the difference between the electric force and the electric field. Let's see. Let us go ahead and got 2 questions about these. And for that, I'm gonna stop my share for a minute. I'm gonna bring up a little PowerPoint here. Okay, so you kind of might have seen the answer for this one already because I couldn't really hide it from you. But let's see. We've got this diagram here. We've got two charges, and they're held near each other. And these charges are going to be released from rest. After being released, the charges move so that the force on the charges increases. Okay, so I'm holding them here, and then I'm gonna let them go. And then they move, so the force between them increases. So with that information, which of these statements is correct? These charges must have the same sign, they have the opposite sign, or it's not possible to determine based on this information. So I will put this up here and I will let you, so I've got the little poll here. We'll just take a poll and see how we're doing on understanding this question. And I think, you know, if your little poll pops up and is in front of this slide here, I think you can use your mouse or your finger to move that poll out of the way while you read the slide. Okay, I'll give us another few seconds here. Got 13 out of 16 have voted. There is a clear winner. Okay, so let's share the results here. Okay, so the majority has it correct. The charges have the opposite sign. Opposite charges are attractive, so those charges are going to want to pull toward each other, and as they move toward each other, our Coulomb force is inversely proportional to the distance squared. If that number on the bottom gets smaller, the force between the particles gets bigger. So that would be this question here. So then you could ask yourselves, okay, what happens if I say, the charges begin to move so that the force on the charges decreases. If the force on the charges decreases, that means that those charges are trying to push away from each other, and that must be a repulsive force, so then they would both have the same sign of charge. So we can tell based on this motion whether or not what those charges are on those things. Okay, well that's good. And then I think I have one more here. Let's see. Oh yeah, I do. So you've seen this already in one of the mini lectures or in the PhysCon. We want to determine the ratio. These are charges with some charge, positive or negative or what. And these are the electric field line vectors. Okay, so based on the direction that these vectors are and how closely these lines are packed, we can determine the sign of Q1 and Q2 and the ratio of Q1 to Q2. So you'll see a similar, it won't be this, but a similar image to this on the exam. So you can think about this question, but I have a poll here to gather our thoughts so we can kind of share how we're doing. There's two questions here. Yes, you found them. Okay. think somebody's got themselves unmuted. I can hear like scrolling or clicking or something in the background there. There we go. Cool. So let's see, we've got 14 of 16 of you have responded. Ooh, okay. Okay, there's 15 of us. All right, well, we'll just end this poll here. And let's see how we did. Okay, this one's a little bit more interesting. So electric field vectors, the electric field vector points away from positive charge and toward negative. So that means that Q2 has to be positive. Field lines are pointing away. And then Q1 is negative. So Q1 is negative and Q2 is positive is the correct answer here. And you see, actually, we're kind of split. So you have to get that in your brain. What's the direction of the electric field, which is different than the electric force vector? Okay. And then determine the ratio of Q1 to Q2. So to find that ratio, I count up the number of field lines. So Q1 has 6 coming out of it. Q2 has 18 coming out of it. So, and the number of those field lines is directly proportional to the magnitude of that charge. So Q2 has more field lines coming out of it. So it has a larger magnitude. It has a larger magnitude by a factor of 3. Q2 is going to be 3 Q1. Okay, so Q2 is equal to 3 times Q1 is the correct answer here. Okay, and you could even rearrange this and you could see, you could do, okay, Q2 over Q1 is equal to 3. That says that Q2 is greater than Q1 by a factor of 3. Okay, so that one we got the majority, which is excellent. All right. And let's see. These slides, if you want to review them, those are up in the electro concepts. There's a whole bunch of other things here that, you know, you actually have seen most of these before in engagement checks, honestly. So, but you can go back and look through them here if you want to refresh your memory, okay, on how those in particular work. So some of these are fair game for what you might see on the exam. All right, so let's go back to our review sheet. All right, so we've got, okay, so we talked all about this electric force and electric field. We talked about electric potential. So I know that, like, even for me, electric potential is a little bit like, okay, I have to think about it a little bit more than some of the other parts. But we want to know the definition of the electric potential and the change in potential. So the electric potential, represented as V, capital V, is the electric potential energy per unit charge. And then the change in potential, or the potential difference, is the, well, it's the difference in potential for a charge between 2 points. Okay? And sometimes I'll represent that as like a delta V. We have to do work in order to move a charge. And so there's equation that goes along with that. The work that we do in order to move a charge from one point to another is negative its change in electric potential energy. And we also showed that the electric potential energy is equal to the charge, the quantity of the charge times the change in potential. So the potential energy you represent as PE, the potential will represent as V, which is the potential energy per unit charge. Okay, so let's see. On your equation sheet, you have under chapter 19, we've got the, well, it's listed as voltage, but the potential difference, or the change in potential, delta V, is equal to delta PE, the change in electric potential per unit charge, divided by Q. We also have the potential due to a point charge, which is KQ over R, not KQ over R squared like it is for the electric field. We want to know the definition of an electron volt, EV here. We have there is a workbook problem about this one. The electron volt is the energy given to one electron to accelerate it through a potential difference of 1 volt. And that's its definition. And we want to understand how to use the conservation of energy and the change in potential to solve for the motion of a charged particle. Now, I'm going to work through an example of this in a minute so that we can understand, so you know what I'm talking about there. Okay. Also, we had a couple of homework problems about that. And then we came to capacitance. So we want to be able to find the capacitance of a capacitor, both with and without a dielectric. So remember, the dielectric is a material you can insert between the plates of the capacitor to increase its capacitance by a factor of that dielectric constant. Now, on your equation sheet, you have the capacitance of a parallel plate capacitor, and it's given as C is equal to kappa, which is our dielectric constant, times epsilon naught, which is the permittivity of free space, times A over D, the area of the plate divided by the distance between the plates. So that kappa there, that's our dielectric constant. If it's just air between those plates, or I don't tell you that I'm using a dielectric at all, then you can assume that that kappa is 1. The dielectric constant for air or a vacuum is 1. So understand how that capacitance depends on the material between the plates, the area of the plates, the distance between the plates. Look at those equations and understand how capacitance changes when you change any of those bits. And we need to know the rules for capacitors in series and parallel. There is going to be a free response problem about capacitors in series or parallel. And so we will talk about these rules for finding the total capacitance, the charge on the plates, and the potential across the plates. And we will work through an example problem. And we need to apply the equation Q is equal to CV to solve capacitor problems. Q is the charge on the plate, C is the capacitance, V is the potential across the plates. And then for our last bit, current, resistance, power. This last little bit here is prepping us to go on to the next unit. But we are going to answer at least one free response question about the stuff in here. So we want to be able to apply the definition of current. That definition for current is the change in charge per unit time, delta Q over delta T. We want to understand how to apply Ohm's law. Ohm's law is V is equal to IR. Understand and be able to use the equation for temperature dependence of resistance. And there was a mini lecture problem we worked through about that. Know how to apply the many definitions of electrical power. So for that, I mean that electrical power can be defined as the current times the potential. It can be defined as the potential squared over the resistance. It can also be defined as the current squared times the resistance. So we can use any of those 3 combinations in order to solve a problem. And so be prepared to be able to use any of those 3 in order to solve a problem. And understand how electrical energy is consumed in your home. That's actually the question that's your discussion for this week. Think about the energy that is consumed by our power usage and how electrical companies might bill you for that power usage. So their energy is equal to the power you consume times time. And your electrical company is going to charge you by that energy that you consumed. Okay. So those are the concepts that we got to get in our brain. And then now we've done a little bit of a refresher, and then we can work through some example problems. So down here are our 4 problems that we're going to have to solve with free response. And you know what? I got to make a bathroom break real quick. So give me like, I'm at home, so the bathroom's just next door. So I'll be right back. So I'll let you read this. I'm going to keep this on the screen, and I'll be just right back. Okay, well, told you it'd be quick. Okay, so let's solve some problems. And I have a list of problems I want to solve here. I don't know how long it's going to take me. I'm sure it'll take me right up to 40 minutes from now, which is 10:40. Might even go past that. I'm going to stop by 11 for sure, so I can go over to my office hours. And also this is your time to ask me questions. So you can ask me questions now too, if you have questions about anything that I've talked about so far. Okay, so the first thing I'm going to do, I'm gonna not necessarily go in order, but maybe partially in order. There was this question, or this statement, be able to apply the definition of current. So, this definition of current that I'm talking about, I is equal to delta Q over delta T. Now, this problem that I'm going to work through, which you might see again on the exam, is a problem from the reading quiz. And I noticed that a lot of students were missing this question on the reading quiz. Usually I don't put, a numerical answer that you have to input on the reading quiz, but I did this one. And actually I went back, and that particular reading quiz that it was from, I think it was 7B, I gave everybody an additional attempt. So if you want to go back and fix it, if you didn't get it right, you can do that. But our definition for current is that it's the change in the amount of charge per unit time passing through some cross-sectional area. So that charge, let's say we have, let's answer this question, which is the reading quiz question. What is the magnitude of the current in a resistor that has 3 times 10 to the 16 electrons flowing through it each second? Okay. So my current, delta Q over delta T, I know then my time was 1 second. So that's easy. This amount of charge that's passing through the resistor per second, that amount of charge, delta Q here, is just going to be the number of your electrons times the charge on the electron. Okay, that's going to be the charge, the amount of charge that's passing any point per unit time. So this is going to be, for this problem, 3 times 10 to the 16, got my electrons, times 1 electron has a charge of 1.6 times 10 to the minus 19 coulomb. Actually, it's negative, that number, but I'm just asking for the magnitude of the charge. And then that's my charge per electron. and I'm dividing it by time 1 second. Okay, so basically I'm just multiplying my number of electrons times the charge per electron. That's delta Q here. So if I take 3 times 10 to the 16 times 1.6 times 10 to the minus 19, that gives me a current of 4.8 times 10 to the minus 3 amperes. And that's 4.8 milliamps. And I think milliamperes. I think the question asked you to report it in milliamperes. Okay, so that's how you solve that problem. That's the very simple application of that definition for current. So you can go back and do that reading quiz again if you need to, because I gave everybody an additional attempt on that. And so you might see a problem like this again. That's a one of your multiple choice questions. Okay. And now I want to talk about how we can think about potential energy in order to solve, or the change in potential energy and the conservation of energy in order to solve for the motion of a charged particle. So I'm going to dump this. Okay. So let's say we have an electron that has been accelerated from rest. So, ooh, this thing is getting sensitive to how much I press on it. So my electron is accelerated from rest. So its initial speed, I'm gonna call it VI, is equal to 0 meters per second. And it's being accelerated through a potential difference. So this is my delta V here of 66 volts. What is the kinetic energy in electron volts? Okay, so this is where we have our definition for electron volt. To solve this problem, this is a conservation of energy problem. And we need to start with our initial kinetic energy of our particle. Oh, this is an electron, so I'll remind myself there. Plus the initial potential energy, electric potential energy, equals our final kinetic energy plus our final potential energy. And sometimes this semester I've been using A for initial and B for final. You can do that too, it's the same thing. We start from rest, so our initial kinetic energy is 0. And I'm going to solve this. So I'm going to move my kinetic energy to the other side here. So I've got minus kinetic energy final equals, and I'm going to move my initial potential energy to the other side as well. Because I do that so that on the right side, I've got my final potential energy minus my initial potential. And that gives me my change in potential energy. Okay, and that equals minus the final kinetic energy. Or I can multiply both sides by -1. So this kinetic energy I'm looking for is equal to minus the change in potential energy. Okay, and so then we have this relationship on your equation sheet that the change in potential energy of a charge is equal to the magnitude of its charge. Well, not necessarily the magnitude, just the quantity of its charge times the change in potential. So my final kinetic energy here is going to be minus the charge on my electron, which is minus 1.6 times 10 to the minus 19 coulomb, times this potential difference that I went through, which was 66 volts. Okay, so then that kinetic energy is 1.056 times 10 to the minus 17 joules. Okay, so that's the energy, but I'm being asked for it in electron volts. So I've got 1.056 times 10 to the minus 17 joules I want to convert that to electron volts. And we have a, on the front page of your equation sheet, it says that the electron volt is equal to, 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. Okay, so the joules cancel. So to convert this kinetic energy from joules to electron volts, I divide it by 1.6 times 10 to the minus 19. And that gives me my energy, kinetic energy in electron volts of 66 electron volts. Okay, so all of that work to show that, so this is, we have the electrons accelerating through a potential difference of 66 volts. What's the kinetic energy? Well, actually we could circumvent all of this and remember that the definition of an electron volt is the energy given to an electron to accelerate it through a potential difference of 1 volt. So we have this electron, we're accelerating it through a potential difference of 66 volts. So the energy required to do that is 66 electron volts. So you could do the problem and then do the conversion and see, oh, okay, that it was 66 electron volts. But here we could just see that we're taking our electron through 66 volts. The kinetic energy required is 66 electron volts because of that definition. So then all of this work, let's see, is kind of similar for another question I could ask. We have a proton this time. So let me get rid of some of this stuff here. We're going to have a proton this time. And it's going to be accelerated from rest, so its initial velocity is 0, to 20% the speed of light. So its final speed is 20% of the speed of light, or 0.2 times the speed of light, which was 3 times 10 to the 8 meters per second. And if you don't remember that, it's on the front of your equation sheet. Through what potential difference did it travel? So in this problem, we're looking for delta V, question mark. Okay, so we can still use conservation of energy to solve this problem here. And let me erase some of this. And actually, all of this stuff right here is good. We've got our initial kinetic energy plus initial potential energy, final kinetic energy plus final potential energy. And we reworked it to show that our final kinetic energy is minus the change in electric potential energy. So this final kinetic energy is 1/2 mv squared. Okay, that equals minus our change in potential energy. We can also write as Q delta V. So here, the next step then, we're looking for our change in potential is to just solve this problem for delta V here. Okay, so solving that problem for delta V would tell me the potential through which this proton had to travel through. We know our final velocity. You can look for the mass of the proton on the equation sheet. Okay, and Q of the proton, that's also on your equation sheet. Now, you know, this will show up in one of your multiple choice questions, okay? So you will not have to fully solve it out as a free response, but and in particular, the question I'm going to ask about this problem has more to do with which equations are you going to use to solve this problem rather than coming to a full, complete answer. So that's one way I can make sure that you understand how to solve these problems, but not asking you to solve them fully all the way through to the end. Okay, so now the next thing I want to do is look through these examples of the problems that you're going to have to work out those 4 problems that you're gonna have to fully work out to the end. Now, I am not going to solve all of these problems top to bottom, okay? But I'll explain how you could solve these problems and ask you to think about a few things on your own in preparation for the exam. And you can always come to me during my office hours if you have more questions about how you might fully solve a problem like this. So okay, so the first one of our free response questions will be able to find the total capacitance of a set of capacitors in series or parallel, and know how to find the charge on the plates of those capacitors. So I'm not going to say whether or not you're going to have series or parallel capacitors, but let's say that I ask you to show that 3 capacitors with identical capacitance can be connected in series or parallel to create a total capacitance. So this is going to be one of our show that problems. So we're going to have 3 capacitors of identical capacitance. And I'm going to ask you to show that they are either some number of farads for their total capacitance if I connect them in series or parallel. So basically you do the work to show me that, hey, this is the capacitance of the total capacitance of these capacitors in either series or parallel. And so let us remember our rules for capacitors in series and parallel, which is different from our rules for resistors in series and parallel. So when our capacitors are in series, that means that they're lined up so that the current has to run through all of them. One before it has to run through the first capacitor before it runs through the second, before it runs through the third. In capacitors that are in series, the charge on the plates of all of our capacitors are the same. The potential across all of them has to add together to be the total potential of our battery that's supplying the current. And we find the capacitance by taking 1 over, we find the total capacitance with this inverse relationship here, okay? And then if our capacitors are in parallel, that means that the current has to split off to go through either one of these capacitors. The charge on all the plates has to add. And so on. The potential is the same across all of them. And the capacitance adds. Like that. It adds just not the inverse relationship, you just add up the numbers, okay? So show that 3 capacitors of identical capacitance have some number of, have some quantity in farads for the total capacitance in series or parallel. So if I ask you that, so what you would have to do is, let's say, okay, if I ask you to find the capacitance for 3 capacitors in series, I would just use, this relationship that I'm boxing in red. If I ask you to find the total capacitance for 3 capacitors in parallel, that's even easier. You just use this relationship here that I'm boxing in green. So these 2 relationships are on your equation sheet, but remembering the charge and the potential on our capacitors in series and parallel, that's not on the equation sheet. So that's the first part of that problem. The second part of that problem would be, let's say, if given V, the potential across each individual capacitor, remember that each capacitor is identical, what is the charge on each plate? Okay, so I'm going to tell you exactly the potential across any one of these capacitors, okay? And you already know what the capacitance is because I'm going to tell you that in the problem. I'm going to tell you the capacitance of each of my 3 identical capacitors. So in order to find the potential across each one of these individual capacitors, you use our equation Q is equal to CV. And then you just solve it for V. So V is the potential across the plates. C is the capacitance of that individual capacitor. Q is the charge. Oh, I'm sorry. I'm going to tell you what the potential is across each individual capacitor. You have to find Q. So you'll know what V is across each individual capacitor. You'll know what the capacitance is of each individual capacitor. And then you could find the charge just by using this relationship. And so that equation is on your equation sheet with all the other equations for the capacitor. Okay, so that's this first problem for the problem solving, the first of the 4. So I'm not going to tell you whether we're in series or parallel, but maybe you want to think about, okay, if let's say I gave you 3 capacitors, each of 1 millifarad capacitance. What would be their total capacitance if they were in series? What would be their total capacitance if they were in parallel? How would you solve that? Okay. Any questions about this? That's be able to find the total capacitance in series or parallel and know how to find the charge on the plates. Okay. Okay, but we'll move on then. So this is going away. So the next question is, or the next of the 4 free response. Be able to apply Coulomb's law to find the electric force between protons and electrons in an atom. Okay, so one of the problems we did in the mini lecture was finding the force between the proton and the electron in a hydrogen atom. So let's think about a helium atom here. I mean, I suspect you all have had some level of chemistry and that you kind of remember like how many protons and electrons are in a particular atom, but I would tell you this information on the exam for whatever atom I want you to use. So a helium atom has 2 protons and 2 neutrons in its nucleus. So this is the nucleus of my helium atom. And then orbiting it, I have 2 electrons. Here's one of my electrons, here's the other. Okay. And my helium atom, okay, there we've got 2 electrons, 2 protons, 2 neutrons. And the 2 protons are separated by a distance of, maybe I'll call that R sub p for the distance between our protons in the nucleus, are separated by a distance of 10 to the minus 15 meters. That's a femtometer, 10 to the minus 15. These are knowns that I would provide to you in the problem. And my electrons orbit the nucleus at this distance. This is the radius of this circle. So my electrons orbit at a distance of 30 picometers, just 30 times 10 to the minus 12 meters. Okay, so that's the information I'll provide you about the helium atom. Find the magnitude. So I could ask you to find the magnitude of the electric force between a bunch of different stuff here. I could ask you to find the magnitude of the electric force between the 2 protons in my nucleus. I could ask you to find the magnitude of the electric force between my 2 protons in the nucleus and one of those electrons orbiting it. You know, different ways that I could ask you this question. So if, let's say, I want to find the magnitude of the electric force between, so the magnitude, we don't care about the sign of the charge, right? The magnitude of the electric force between the 2 protons in the nucleus and my 1 orbiting electron. So we've got our 2 protons and my 1 electron. I want to find the magnitude of the electric force between them. So I've got my equation for the electric force. That's my Coulomb constant K times the magnitude of my charges in the nucleus times the magnitude of my electron that's orbiting it divided by their distance squared. Okay, so K is our 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. So if I'm finding the magnitude between the 2 protons in the nucleus and the 1 orbiting electron, this quantity that I have here for Q1, okay, that's going to be both those protons. We can pretty much, you know, they're together in the nucleus there. So we've got our 2 protons, and the magnitude of the charge of those 2 protons is 2 times 1.6 times 10 to the minus 19 Coulomb. The charge on 1 proton is 1 times 10 to the minus 6 Coulomb. The charge on 2 would be 2 times that. And then my electron orbiting it, well, that has a magnitude also of charge of 1.6 times 10 to the minus 19 Coulomb. Okay, I'm just looking at the magnitude, so I don't care about the sign. And then I divide by the distance squared. So those protons are separated from the electron by a distance of 30 times 10 to the minus 12 meters. And then I have to square it. Okay, that will give us the magnitude of our electric force, 5.1 times 10 to the minus 7 newtons. Okay, and since my protons are positive, my electrons are negative, that's an attractive force. Those want to come together, right? But I could also ask you the same question, but ask you to find the magnitude of the electric force between the 2 protons in the nucleus. And if I asked you to do that, you know, you've got the charge of one of your protons, the charge of the other proton, and then the distance between them is the smaller distance of 1 femtometer. And since they're positive charges, they're going to want to repel each other, right? So there's a couple of different ways I could ask you this, and it's not, I might not necessarily ask about the helium atom. I might give you another atom, but that is how you'd want to approach it. Okay, the force, be sure you're using the equation. If you see electric force, okay, or Coulomb's law or anything like that, you want to use this equation right here, right? K Q1 Q2 over R squared. Well, that's being able to apply Coulomb's law to find the electric force between protons and electrons in an atom. So the neutrons are neutral, they have no charge, so it doesn't make sense to ask about the magnitude of the force with those there. Okay, any questions about that? Okay, so I would, So doing most of the, writing out the equations, putting in the numbers, showing me that that process is the majority of your points here, right? If you get to this step, if you get to this step right here, and you plug everything into your calculator wrong, okay, and then you don't find this number here, but you showed me you know how to put everything in the equation in the right way up here, you're really only going to lose 1 point, okay, with this new rubric they have. So the majority of the points go for you showing me the work. And then if we get to the last step and you buggered up how you type the things into your calculator, then that's only a very minor point deduction. All right. So, but still, you should practice, how you put these into your calculator, and you want to think about is this answer reasonable? This number is pretty small, but if you're finding that magnitude of that force between the protons, you might think it's a little bit big, and it's repulsive. They want to push away from each other. They want to push away. But there's another force that maybe we'll talk about later in the semester, that the name of that force is the strong nuclear force, and it binds neutrons and protons together in the nuclei of the atom, and it keeps the protons from flying apart, because they're so close together. So anyway, that's just another additional aside. So the magnitude of the force between our protons and our electrons is different than the magnitude of the force between the protons on their own. Okay, any questions there? Cool. And then our third question, free response. Ooh, be able to find the electric field. Okay, so it's clear to me that we're definitely going to go over 1040. So you all do what you need to do. This recording will be up. I'm gonna go until 11 here, okay? For our exam review. Next question for a free response. Be able to find the electric field, both the magnitude and direction, at some point due to the presence of a charge. So this problem, we will have to deal with vectors. We're asking for the electric field, both the magnitude and the direction. We did a mini lecture problem about this. You had a homework problem about this. You are going to have an exam problem about this. So we are not going to deal with multiple charges. We're just going to have one charge, okay? So let's say we have put this right here, a 5 nanocoulomb charge. Here, let me draw that again. This, my pencil's being a little bit weird today. So we have a 5 nanocoulomb charge at the origin of a coordinate system, like so. Okay, so this is 5 nanocoulomb. What is the magnitude and direction of the electric field at point P? Point P has a position of x equals minus 2.1 meters, and y is equal to minus 5.2 meters, question mark. So we need to find the electric field at that point. Okay. So if I look over here at my charge, I kind of drew an XY axis here. So this is a positive charge, okay? And we saw what the electric field looks like around a positive charge. The electric field vector points away from positive charges. So all around this positive charge, the electric field is pointing away kind of like this, okay? But I want to find the electric field at this particular point right here. So if I come in here, look at my system, and let's place that point on here. And that point is at minus 2.1 meters on the x-axis. So we have to go over this direction. This is minus 2.1 meters. And the y position, we have to go down 5.2 meters. Okay, so that means that this is my point right here, defined by an x position of minus 2.1, a y position of minus 5.2. At that point, we have to find the magnitude and direction of the electric field. Now, if I go ahead and draw in my electric field vector, that electric field vector is pointing away from my positive charge. The electric field vectors point away from positive, along this same line that I can draw from my positive charge to that point. So if you kind of look in here, I've made a little triangle, and that has legs of 2.1 meters and another leg of 5.2 meters, and there's this hypotenuse there. So along this hypotenuse pointing away is the direction of that electric field vector. All right, and then so this is my direction of my electric field vector. So I've drawn in that vector. I have to find its magnitude, and when I say the direction, I have to find its angle with respect to the positive x-axis. But first, let's deal with how we find the magnitude of that electric field. Okay. So my electric field, due to a point charge, magnitude of it, is just K, my Coulomb constant, times Q all over R squared. So my Coulomb constant is 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. I'm going to multiply that by the charge, which is 5 times 10 to the minus 9 Coulomb. That's my nanocoulomb. So I'm also going to expect that you remember that nano is 10 to the minus 9. Okay. That's in the, you had to remember that for last exam as well, because we had our nanometers. And then we divide this by R. R is the distance between my charge and the point where I'm evaluating this electric field. So here, ooh, didn't draw that very well. Let's use this. So this distance right here is R. Okay. This is the hypotenuse of that little triangle that I drew there. Okay. So we could use Pythagorean theorem. R squared is equal to x squared plus y squared. So R is equal to the square root of x squared plus y squared. So that distance is, got 2.1 meters squared plus 5.2 meters squared. Square root that. So this distance is 5.61 meters, okay? So the point at which we're evaluating this electric field is 5.6 meters away from the charge. That's my value R. This is 5.61 meters squared, okay? So the magnitude of my electric field is 1.43 newtons. Okay, but we're not done. Now we have to find the direction, the angle from the positive x-axis. So what could we do for that? Like in the homework problem, in the problem we worked in the mini lecture, the point where we were evaluating our electric field was up here in the first quadrant. So that angle is just this little angle here, theta. So that one was a little bit easier. But here, I'm looking at my electric field vector. I could draw another little coordinate system right here at point P. Now I have to go all of this way from the positive x-axis. I've got 180 degrees from the positive x-axis plus this additional little angle here. So if I want to report my angle from the positive x-axis, what I could do is I could find this angle theta here and add 180 to it. This angle here is the same as this angle here. Okay, because these are kind of equivalent triangles that I could draw in here. So I could use tangent theta equals opposite over adjacent, opposite side over adjacent side in order to find this angle theta. So tangent is, or theta is the inverse tangent then of my opposite side, which was 5.2 meters, over my adjacent side, which was 2.1 meters. Those cancel. I don't need to put the positive or negative sign on here, since I'm just looking at the geometry. So that little angle theta was 68 degrees. So this is the angle, let's see, let me draw that, write that again, 68 degrees, okay? So that's, this angle below the x-axis. But to get that entire angle from the positive x-axis, I would have to add 68 degrees plus 180. Okay, and then that would be 248 degrees. So my full answer here would be an electric field of 1.43 newtons at an angle of 248 degrees from the positive x-axis. Okay, so if you just give me the magnitude and you don't tell me the direction, you're not going to get the full points for the problem, since I have to know both. I need to know everything about this electric field vector, the magnitude of the electric field, and the direction that this electric field vector is from the positive x-axis, because that's how you fully define a vector. Now, in your, so in the mini lecture in the homework, we found the electric field at some point up here. Now we just did this example where we found the electric field at some point in the third quadrant. This is the first quadrant, this is the third. But maybe think about how you could find the magnitude and direction of the electric field vector if it were over here in the second quadrant or down here in the fourth quadrant. You still have to find the magnitude of your field and then think about how you would report your angle of that field vector from the positive x-axis. Okay, so I'm not going to tell you, where this electric field vector is going to be located. So you have to be able to be flexible to figure out, how you would report your electric field vector, depending on which quadrant it's located in. Okay. Can I answer any quick questions about that? Oh, okay.
I do have one question.
Yes.
Is there a specific mini lecture recommendation that you would ask, that you would say might have this in it?
So the mini lecture is us doing the first quadrant. And I can figure out real quick which one it's in. I need to create like a little map. It's like a treasure hunt, isn't it? To find all of these. I understand that. Electric fields. I believe it is in 6A. Okay, engagement, concept engagement 6A. It's yeah, it's 6A, and I think it's don't remember. Oh, I'm forgetting where it's located. Let me look. I know it's in week 6. Let me look there at those videos. Yeah, okay, let me, I will look through and remember which exact video it's in. I can't remember off the top of my head anymore. Okay, but we did do it in one of the mini lectures. I think it's one of the 3 in 6A, but I will go back and find it and make an announcement, okay? Or maybe I'll note it. I'll put a little note next to it on the page where where I have the study guide. How about that?
Yes, ma'am, that works.
Okay. So I didn't do a very good job of mapping it out, but we did do it in there. Okay. So now let me do the final one here. Okay. So this one, the question I'm going to be asking you here, you know, is a little bit different than some of the homework problems that we worked through, but it really tests how well you kind of grasped this material. So the question is, be able to apply Ohm's law and the temperature dependence of resistance to find the power dissipated by an electrical device. So I'll read the problem here. And in this problem on the exam, I give you some additional hints to help you walk through the problem too. But let me read this problem here. We have a wire made of an unknown alloy, and it has a temperature coefficient of resistivity of 8 times 10 to the minus 3 degrees Celsius, that's the minus 1. A potential difference of 100 volts is applied to the wire. Okay. It initially carries a current, so its initial current is 0.5 amperes when the wire is at a temperature of 20 degrees Celsius. The wire then quickly heats to 80 degrees Celsius. It's going to have a final temperature at 80 degrees Celsius. At this final temperature, what is the power dissipated by the wire? Okay, so to solve this problem, you're going to have to use Ohm's law and our temperature dependence of resistance, which you all just learned about on Tuesday, and then our equations for power to solve the problem. Okay, so our first step will be to find our initial resistance at 20 degrees Celsius. Okay, I know my potential. I know the initial current. So I can use Ohm's law, V is equal to IR, to find the initial resistance. Resistance is equal to V over I. Now, you know, once you guys do the workbook 6, you know, this problem won't be as foreign to you because I know you just learned about this stuff yesterday. So the potential that's being applied to this wire is 100 volts. the current that's initially running through this wire was 0.5 amperes. So my initial resistance is 200 ohms. Okay. Now, because of our temperature dependence of resistance, that as that wire heats up, its resistance goes up, which means that it's going to change the power that that wire can dissipate. It's going to change the current that's going to be able to flow through that wire. So step 2, we want to find the final resistance at 80 degrees Celsius. So we have our equation for the resistance is equal to your initial resistance times 1 plus our temperature coefficient of resistivity, which is a property of the wire, times T final minus T initial. So your equation sheet calls this delta T. That's just T final minus T initial. So then this will equal, we've got our resistance over here that we found originally, 200 ohms times 1 plus, we've got our temperature coefficient of resistivity, 8 times 10 to the minus 3 inverse Celsius. And then we multiply it by the difference between the final and the initial temperature, 80 degrees Celsius minus 20 degrees Celsius. Okay, when we do that, we find that, so you have to do 1 plus all of these things multiplied by each other. So you would take 80 minus 20 and then multiply it by the temperature coefficient of resistivity, and then add it to 1. And so that final resistance is 296 ohms. Okay. So then in step 3, we can find the power dissipated by this wire when it has reached the 80 degrees Celsius. Okay, so in order to find the wire at that hotter temperature, we had to find the resistance of that wire at its final temperature. And we could only do that by using our equation for the temperature dependence on resistance. And for this value R naught, the initial resistance, we had to use the potential and the initial current running through the circuit. So P is IV, it's V squared over R. It is I squared R. So you could use any one of these to solve the problem. I would probably use the middle one here because we already know the potential applied to the wire, which doesn't change. And we just found the final resistance was 296 ohms. And then that will give you the power dissipated by this wire, which is 33.8 watts. Okay. Now you could use either one of these other two and get the same answer, but you'd have to find the final current. So the final current would be taking V is equal to IR and solving it for I. So I is equal to V over R. So that's still our 100 volts, which doesn't change. That's constantly being applied to the circuit. And then we divide it by our final resistance, 296 ohms, and we find that the final current is 0.338 amperes. So the current is reduced when you have a larger resistance. You could use that current in the other two expressions for power to get the same answer. So this problem is a really good example of how you can use Ohm's law, power dissipated by the device, and the temperature resistance, temperature dependence on resistance to solve one problem. You have to fit all those pieces together. Okay, so if you break it up into these chunks, it makes it a little bit less stressful, I guess, to solve it. And I'll tell you that for this problem on the exam, I'm giving you like the steps to help you work through it. But this is an example of how you would attempt a problem where you apply Ohm's law and our temperature dependence of resistance to find the power dissipated by a device, combining all of those ideas together from our very last set of lectures, which is what you all looked at yesterday. Okay, yesterday and Tuesday. So that's it. I know it is a lot. Yeah, it's a lot. But I've given you a lot of hints to help you do the best that you can on this exam to really test what do you all, how well have you grasped the material. So I will go back and I will make sure that I connect which mini lectures you should go to for some of these 4 problem-solving problems, because even I have forgotten where some of these live. And yeah, so that you can do that. And you never know where that electric field where I'm going to ask you to evaluate it at around that charge. So you want to think about, how would you solve it depending on, are you in the first, second, third, or fourth quadrant for that point? Okay. So this is our opportunity to really pull together everything that we've learned over the past month. That's what tests do. They pull together all that information and help us synthesize it in one chunk. So that's what we're doing here. And I know that a lot of you are aware of some of you are in organic and you have this exam that's just mine is sandwiched between yours. So I just want you to know that I am here for you to ask me questions and to help. I can even help you on your exam revisions if you want that too. Okay. So unless y'all have any questions, I guess if you have questions, you might as well join me over in my virtual office hours, which I'm going to start here at 11. Okay, so that's it. That's all I have for you here.
All right, I would stay, but I have to drive to campus. I'll see you later.
Okay.